I'll be presenting two foundational quantum algorithms for today's video, the Deutsch-Jozsa algorithm and the Bernstein-Vazirani algorithm, which are two very similar but distinct in its own way, with dealing with specific tasks. They are among the earliest of the algorithms to demonstrate how quantum computing could outperform its classical counterpart. Although they don't yet provide practical speed-ups over real-world problems, these algorithms are essential because they lay the theoretical groundwork for more advanced quantum algorithms, like Shor's and Grover's. In 5 minutes, I'll walk you through what these algorithms are, how they work, and how can be implemented using Qiskit and Python. But before we dive into these algorithms, I will assume you are familiar with foundational concepts of computational theory, quantum mechanics, and linear algebra. Imagine you're given a mysterious black box. You can feed it numbers and it gives you back either a 0 or a 1. It will either give the same answer no matter what number you put it in, or it gives 0 or 1 half of the time. If you were using a normal computer, you'd have to test a bunch of numbers, possibly more than half of all possible ones, to be sure which type of box you're dealing with. But with a quantum computer, thanks to the Deutsch-Jozsa algorithm, you can figure this out with just one test. Classically, a computer tries 2 to the n-1 plus 1 times to tell if a function is balanced or constant, in the worst case. For a quantum computer, it only needs to try once, since quantum computers use qubits which can represent 0 or 1 at the same time. This lets you test all the inputs in parallel using something called superposition. The general circuit for the Deutsch-Jozsa algorithm is shown. The first register is initialized to be ket 0 of n qubits. The second register is initialized at ket 1. This is done using an X gate or a NOT gate. First, we apply a Hadamard gate to each qubit of both registers. Then, we apply the quantum oracle of our choosing to test whether they are a balanced function or a constant function. Thirdly, we must apply a Hadamard gate to each qubit of the first register, then perform a measurement. Now we go to Google Colab to demonstrate the Deutsch-Jozsa algorithm with 3 examples. Suppose we have a quantum oracle shown as shown. Thus, we put it in the Deutsch-Jozsa algorithm. Then we measure it using the AER simulator with 1024 shots. Then, the histogram showed that we have an output of ket 111, meaning that the function is balanced. Now suppose we have an identity gate on the second register as our quantum oracle. Then, the Deutsch-Jozsa Deutsch-Jozsa circuit is shown. After simulation, we found out that the histogram gives an output of ket 000, indicating that the quantum oracle is a constant function. Lastly, we have a test circuit of unknown we don't know yet if it is a balance or not. So, suppose the test circuit is shown. Then the quantum Deutsch-Jozsa algorithm circuit is as shown. Simulating it gives a ket 111, indicating that the test circuit is a balanced function. The Bernstein-Vazirani algorithm solves to find a secret key in the same manner that the Deutsch-Jozsa algorithm works. Only this time, the second register is initialized to ket minus rather than ket 1. Otherwise, all the steps implemented on the Deutsch-Jozsa algorithm is also done here in the Bernstein-Vazirani algorithm. For demonstration, suppose our hidden number is 101. It is represented by this quantum oracle shown below. Then, it fits to the Bernstein-Vazirani algorithm. At last, when we simulate it, we found out that it indeed showed in the histogram. To end, this is a Venn diagram comparing and contrasting both algorithms discussed in this video. See you next time!